Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about another coordinate system that's very closely related to polar coordinates. So to kind of motivate that idea, just think about this question. So if we let polar coordinates basically extend up into z with no restrictions, what shape would we basically get? So I'm saying we've got, x, y, z, and we've got polar, right, which gives us like a circle down here. And, it's probably not that hard to see that if we just let this extend into z, right, everywhere, no restrictions, right, we would basically just get a cylinder, right? And so this is actually a useful coordinate system, and the way it literally is called cylindrical coordinates. And coordinates. And basically you keep the polar part, so x equals r cos still, and y equals r sine theta, and then you just let z equal z. And so this is useful basically in triple integrals. That's where we're going to see it. And basically if there's a triple integral region that kind of looks like circular, but 3D that we're integrating over, like a cylinder kind of region, right? Then it might be useful to switch to this coordinate system. So you literally just keep, it's kind of like a hybrid between rectangular and polar. That's kind of how I think of it. So just to kind of give you like a sense of converting this way, I just want to do this problem. So if we were to plot the cylindrical coordinates 2 pi over 3, and 1, we would get this, right? Because it's saying we've got a radius of 2, so it's coming out, right? So this is, the r down here in polar. So we're coming out 2, and we're rotating from here 2 pi over 3, and then z is just 1, right? So you would get that point. And just to show you kind of how we could convert it to rectangular, so in cylindrical, that is actually the order we always write things into. We always go r theta z, basically, is how we do it in cylindrical coordinates. And if I was going to convert it, we know x is r cosine theta, right? So x is 2 cosine 2 pi over 3. And so that would be 2 times negative a half, or negative 1, right? Which you can kind of see if I bring this back. This x coordinate is negative 1. That's what it's saying. Then y is r sine theta. So y is 2 sine 2 pi over 3. And so y is 2 times root 3 over 2, which is root 3. And so, it's hard to see, but basically this comes out in the y direction. Not quite as parallel as I wanted it to be. It's a little better. So this is supposed to be root 3. So if you go negative 1, root 3, 1, right, you should get to the same point as that. And so we should be able to convert backwards too. So down here, I want to find cylindrical coordinates for the rectangular coordinates 3, negative 7, okay? And basically you need to think about how to get, you have, I guess, part of it, right? We know, based on this, that z is negative 7. We really just need to use the x and the y here to figure out how to get r and theta. So if you think about, I think the theta one to me has always been a little easier and more clear. Like if you think about what things in math relate x and y with an angle, you should kind of get to tangent pretty quick. So if you think tangent, right, of this theta angle is going to equal 3 over negative 3, or just, negative 1. You can just kind of think a little bit of trig here. So I always do the, So I always use the acronym all students take calc to remind me like where things are positive, right? All of them are positive here, sine's positive here, tangent here, and cosine here. So if tangent is negative, then that means that I can't be here and I can't be here, right? So I'm either in quadrants 2 or I'm in quadrant 4. And then you can just go and look at this point right here, you know, the XY stuff, right? So we know we're going 3 and then negative 3 in the Y, right? So my point is like over in the 4th quadrant. So then you can just get it from there. You know, then you have to be basically, this has to be pi over 4 right here. So theta is, I guess, a negative pi over 4, right? Because we're going backwards, you know, around the unit circle. So that's my angle. And then I just need to get r, and I can just do that with like, you know, something like this. So I can do either x or y, doesn't matter. Let's just do x. So using x equals r cosine theta. 3 would equal r cosine negative pi over 4. And so negative, what was it? So cosine of negative pi over 4, right, is going to be root 2 over 2, right? So we have 3 equals r root 2 over 2, and then you can just kind of move things around. You get 6 over root 2 is r. So one polar coordinate with this thing would be 6 over root 2, negative pi over 4, negative 7. That's definitely a correct answer, but you know, you can definitely get this angle to be other things, because really, you know, you could have spun around a full 2 pi more, right? So you could say plus 2 pi here or something like that, or like even plus 4 pi, right? So there's multiple polar coordinates. I'll get you to a rectangular coordinate. So when you do this, it's a little weird to write the answer. The best way to write it is honestly to just say like, you can add 2 pi n to basically this thing. But this is definitely an answer. And another way that you can actually get the r, if you want, right, is basically just utilizing the fact that x squared plus y squared is equal to the radius squared, right, in polar, right? So what you can do is you can also get r first if you have x and y by just solving that, right? And you know it's just the positive one because it's a radius. So that's another way to do it, but you can also start here with the angle and then like solve this out. So r kind of you can do in 2 ways. All right, so some equations in cylindrical coordinates look kind of funny. So if you think about trying to describe the surface whose equation is just like z equals r, you would see that you actually get something pretty familiar. So one thing to note, z equals r is actually always going to be positive, right? Because r is always positive. So we can't get anything negative with our graph. And you can also use what I was just talking about previously and think about, you know, r is square root of x squared plus y squared. So if you want, you can kind of get a visualization of this if you can like understand what that would be. But another way to just think about it is literally just kind of get into like this part right here. So what it's saying is that for every amount you go up, you go over that same amount, right? So those are equal things. And then if you go up this much, you go over the exact same amount. If you go up all the way to here, then you go over to here, right? And what this would give you is basically you would have the kind of upper part of a cone here. So like this part wouldn't be here, and that's because of the positive part. But you would have everything up here, and it would be this nice, looks pretty messy. You would have this nice kind of circular structure, right? Because it's the amount you go up is always equal to the radius, right? So whatever the radius is of the circle, you've gone up that much amount. It's like very symmetrical. You're not getting like weird elliptical kind of things, or like it's super skinny or something like that. But yeah, you would basically get like an ice cream cone kind of shape. That's what z equals r is. And you can also think of it just, if you think of z equals x squared plus y squared, and then imagine what happens right when you square root, you just get the positive part. So that's another way to think of it. All right, so for our purposes, probably the most important thing is that we understand what like dv is going to look like, and also what it's equal to. So the idea with this is that basically we're going to run into things where it sort of looks cylindrical, the thing that we're integrating over for a triple integral, and so we need to have a handle on what dv is for this. So basically, again, it's just like, when we did polar, we thought, okay, we have like, some sort of angle, right, theta, and then we've got this kind of chunk out here, right, which is what we were integrating over, right? We were probably, I think we called it like, region D or R or something like that, but this region, we still figured it's kind of area, this is like the dA. We still figured this out basically using length times width, but we had to just like add in a little bit of a little change because there was an arc length part in there instead of just like a full-on rectangle. And so we did arc length of that part times the change in the angle, right? And that's how we got dA before. I guess it's good to also just write what we got, right? So we got that dA before was r dr d theta. I used it a lot, but it's good to put it down. So we had that part before, and really now, right, it's very similar. If we want to do volume of a region, right, we're literally doing like length times width times height. And so, length times width is literally coming from, this part is like the dA, right? And then we're just scaling it by the height. So since this part we already solved over here, we can start by putting that in r dr d theta. And then the height is just the change in the z, right? So we literally just need to tack on a dz. So the only new thing here is this part, which we just tack on dz. And for whatever reason, a lot of times what you'll kind of see is basically dv written this way. So you'll see r dz dr d theta. Same thing, right? Just putting the dz kind of in the front there. But don't look at it as anything other than really length times width times the height. And the length times width comes out of this. And then the height change is just dz, right? So that's what we're going to use to help us do these integrals. And so now I just really want to do one of them. So I want to evaluate this triple integral. And I'm going to start by sketching basically what this problem wants us to integrate over. And then you'll see that it's like a cylindrical problem. And then we'll just solve it. All right, so I'm just going to look at the bounds, basically, right? So first we got z equals square root of x squared plus y squared, which is really like one of those z equals r things. So that's going to be like the upper part of a cone. So I'll do my best to show this. We'll do these first bounds in red, maybe. So we have like a cone, right? It's very nice and like symmetric with every time you go up, you could just go over that same amount. I'm going to try to make that a little bit better. There we go. And then it says we go up to z equals 2. So the upper bound, where it's cut off is like a plane, right? And this plane is up at a height of 2. So that's, we're going from 0 up to 2, just based on that first part. So this is like a circular cone. And then here, the bounds say y equals square root of 4 minus x squared or negative square root of 4 minus x squared. So let's just do this in yellow or something. So y equals square root 4 minus x squared is the same as like y squared equals 4 minus x squared, or x squared plus y squared is 4, right? So you're basically getting a circle right there. So it's saying that you really, really what's happening is it's saying y equals the positive square root, and you would get this part, right? If this is going back in x, and then y equals negative square root, we get the other part. So we're getting a circle down there. Might do this dotted behind. So we're getting a circle down there, and then x is running from negative 2 to 2, right? So I guess negative 2 is back there, and 2 is right there. So that is roughly what I'm integrating. And so it's the solid that's kind of in this cone region that's cut off, right? It's cut off up at 2. And definitely a good cylindrical problem because it's got some sort of like polar planar part down there. And then we're just letting it go up into z, right? And so it makes sense to use cylindrical. So it all makes sense to definitely convert it to polar, because that's like whenever you do cylindrical, that's really what's going to happen, right? And if you convert this thing to polar, right, x squared plus y squared is r squared, and then you will have another r, right? And then we're going to have dz, dr, d theta. So this part is all just coming out of v. It's all just coming out of dv. And then we're going to go from r, right? In z, we go from r, this thing is r, and we go up to 2. And then in the radial region, right, we're going from 0 out to 2. And then the angle is a full 2 pi, right? And, if you want, it's one of those two where there's nothing in here that has to do with angles, right, when you integrate. So you can just honestly do like a 2 pi times this problem. And now, I'm also going to do r cubed, and then dz dr. So now it's just a double integral, if you want to think of it that way. So integrating this thing, we're going to do, in z, we just literally tack on a z, and then we're going to do 2 minus r for that z when we plug it in. And then nice integral from here. You're going to get like 1/2 r to the 4th minus 1/5 r to the 5th. Actually, I'm going to go 0 to 2. And then if you just simplify all that out, you get 16/5 pi. That's it. So basically, if you see something, a triple integral problem that has like x, y, or really any planar polar structure to it, so if it's circular in any of the projections onto any of the plane regions, but then you in the other direction, like here in the z direction, it just kind of looks like whatever and just goes up in z, then that's where you should use cylindrical. So it's basically a way to deal with triple integrals or higher, and where you have planar polar structure and then like just some sort of like scaling up in z, or really any direction at all. All right, and that's basically it for cylindrical.